Hello, Assalamu alaikum students. It's been a long time, but today I'm back with another topic. Today we're going to be studying about an object falling on an inclined plane with and without friction. So this is the basic body diagram of the object. It may look complicated at first, but I promise you that it's really easy. You just have to focus on what I'm teaching and just listen carefully. So for better understanding and for more constructiveness, I'm going to erase this figure and draw it from scratch so that you can replicate me and you can put it in your copy. And by the way, this is part of physics first paper, chapter 4, Newtonian mechanics. So, to make you understand first, let's do a real life example. You see, this is a plane. This is a plane right here, and this is another plane. Are they both straight with each other, or are they both at 90 degrees with each other? No, they're not. They're at a certain angle with each other. You see? They're at a certain angle with each other. This is what we call an inclined plane. This plane is now inclined. At what? At this angle. We call this angle here theta. Okay, so now when we put an object on top of this inclined plane, we observe that the object falls down. Why? Why does it fall down? It falls down because we normally know that an object will fall down because it has gravity, the gravitational force working on it. So we know that gravity works perpendicularly. But when we put this on an inclined plane, we'll get to this later, but only the whole gravity does not work on it. Only one of the components of gravity works on it, the sine component. Okay? And we know that sine is proportional to the angle. So the larger the angle, the greater the value of sine is. So when gravity is multiplied by sine, g sine theta, the more the angle will be, the more the speed or the acceleration of the object will be. We can also see this in real life. For example, if my plane is straight and I put this object here, the object falls straight down at 9.8 meter per second acceleration. But the more I tilt it, let's say here, the less acceleration it had. And so, if I put it at even further angle, the less steep it is, it rolls at slower acceleration. And so if I keep doing this and I make it completely horizontal, the object has no acceleration at all. Why? Because if I take this plane again, because it has a 0 degree angle with the second plane right now. And since sine 0 degrees equals to 0, so g sine 0 is equals to 0. There is no acceleration at all. So the fundamental thing is, the more the angle of this is, the angle of incline, the faster the object will fall. That is the basic theory. So now let's try this on the board. At first, we will draw the inclined plane. We just saw right here, this one, okay? So, we drew the inclined plane. Now what do we have to do? We see that there is an angle here. We draw the angle. We consider this angle theta. You may consider it as alpha, beta, gamma, sigma, anything you want. Now what do we do? The third part is, we put an object right here. We draw the object on the table, on the inclined plane in our board. Here. This object obviously has a center of mass from which the components act All components act from the center of mass of the body, not from the edges of it, okay? So we put the center of mass right here. And now we do the things that aren't visible in real life. We draw the forces working on it. So what forces are working on this object right now? Obviously, the gravitational force, which always acts perpendicularly to the body, always straight down, not right, not left, always straight down. Okay. So we drew the mg. Now, from vector, we know that acceleration is a vector component. Acceleration is a vector component. So we know that vector components can be divided, vectors can be divided into their components. So for example, if this is a vector, we can divide it into perpendicular components of x-axis and y-axis. This is y, this is x. Then this would be the x component of acceleration, and this would be the y component of acceleration. And we know that this would be equals to a sine theta, and this would be equals to a cos theta, right? Okay. Similarly, we're going to do the exact same thing here. We'll just divide this into components. So, one component here, and another component right here. Sorry, this isn't a straight line. So the question arises, which will be the sine component and which will be the cos component? So which one is the x-axis and which one is the y-axis? Here, we first have to consider what angle we are taking, right? Because we're taking the angle for mg, we're considering mg, and theta is here. So what angle are we really working with? It's really simple if you think about it. This is 90 degree, and this right here is also a 90 degree. So, but let me use a different marker. So if you think about it, this angle right here, sorry, not this, if you think about it, this angle right here, since this is 90 and this is theta, this must be 90 minus theta, because all angles sum up to 180 degrees, right? And similarly, let's just extend this. For this angle here, this is a 90 degree. Well, no, this is not a 90 degree. This is a 90 degree, right? So since it's okay. This is a 90 degree. So since this is 90 minus theta, for this, in order to be a 90 degree, this must be also theta. Because theta minus 90 plus theta equals to 90. And this will be the angle. So this must be theta. So if this is theta, this is also theta. Okay? Okay. So the takeaway is that the angle of incline between the two planes is also the angle between mg and mg cos theta. Between mg and this, I'm sorry, not cos theta. Now we consider which one is the y-axis and which one is the z-axis. Since we know that the object is rolling here and the object will fall, the object is rolling in this direction, but if it is thrown freely, the object would fall downwards. So what is the downwards of this? The downwards is this, right? the downwards is this and the x-axis is this, or if the downwards is this and the x-axis is this and the downwards is this. Because if I remove this plane, it's gonna fall downwards this direction, not that direction. So that's why this is the x-axis and this is the y-axis. So for the y-axis, we obviously write mgy, and this is mgx. And we know that gy would be g cos theta and gx would obviously be g sin theta. So we just directly write that in the figure. So here it's gonna be mg cos theta, and this is going to be mg sin theta. Okay, everything is falling apart. Okay. Now observe another thing. Let me just bring that again. When I put this object here, when I put this object or this bomb right here, lip balm, on this inclined plane, we observe it only goes downwards, but it doesn't go upward. No matter how flat the angle is or how steep the angle is, it doesn't have any acceleration in the upwards or upwards direction, or the downwards direction. Downwards is this, because we're considering the x-axis is here and the y-axis is here. They're perpendicular to each other. The object is only moving. Wait, how do I? Oh, no problem. The object is only moving towards the x-axis. It is not moving towards the y-axis. It is not moving upwards. It is not moving downwards. If we consider the x-axis as this, then it is only moving towards the x-axis. It is not moving towards the y-axis. So since it is not moving towards the y-axis, it doesn't have any acceleration towards the y-axis. And if there is no acceleration, there is no force. So, since we have established that there is no force on the y-axis, but we observe that there is an mg cos theta, there is only a single force acting downwards. So for a force to be zero, there has to be either no force applied at all, or there has to be two forces that are equal and opposite in nature. We clearly see that there is a single force being applied here, but we also see that the object doesn't move in the y-axis. So there must be another force that is equal and that is opposite to mg cos theta. And there is actually. That's what we call the reaction force of the object. Where does this reaction force come from? This reaction force comes from the third law of Newton, which says that every action has an equal and opposite reaction. This object exerts a force mg cos theta on the table, and the table exerts an opposite and equal force, that is the reaction force, on the object. These two are equal in nature, and these two balance each other out, and so the Fy or the y-axis has no acceleration at all. Okay, so we've established the key components of this system right here. The rest of it is pretty easy. It's just basic maths and basic physics. So let's start with the most fundamental equation of physics, which is F equals to ma. Okay? Okay. So what does F equals to ma say? F equals to ma states that if there is any force applied, there has to be an acceleration of the object towards that direction. If we consider this a vector, then it would be better. If there is any force applied, then there will be an acceleration in that direction. So using this, we can write out some equations based on the basis of our previous discussions. we assume that this object is falling downwards at an acceleration a. Okay? This body is falling downwards at an acceleration of a. So we know that F equals to ma. But get this, force is also in vector quantity. So is there any reason to think that force cannot be divided into x and y axis? There is not. So we can also divide the force into x and y axis. So this is the force along the x axis, and this is the force along the y axis. Well, you don't have to. Well, let's just put it. This is the force along the y axis. Okay? Okay. So now we write out the equations for the f along the x axis and the force along the y axis. So what is this? This means that the summation of all forces, remember, Newton's second law is only applicable for the resultant force, or the sum of all forces working on a single body. So the sum of all forces working on the x-axis is equal to the mass of an object. Let's assume the object mass is m. M is equal to the mass of the object times the acceleration along that axis. In this case, the x-axis of the object. So let's assume this is along the x-axis. So this is ax and this is ay. Okay? Okay. So what is this? This is the force along the x-axis. The summation of all forces along the x-axis is equals to the mass of the object times the acceleration of that object along that axis. This is one part. And now let's consider the y-axis. No reason, it is the same. The summation of all forces along the y-axis is equal to the mass times the acceleration of the object along that axis, in this case the y-axis. So this is also there. This should be the starting line of every single physics math you do involving any type of force, because from this you'll be actually able to get the concept very clearly on what objects, on what forces are acting on the object, and and what sign to use, minus, plus. Everything is really clear if you start from here. This is the basic pillar. This is the pillar on which you'll build your building. Okay? Okay. So now let's divide these two segments. Divide these two segments with a red line. Let's start with f of x. So what do you see on what forces for this part? What forces do we see on the x-axis? Take a minute. Take a few seconds to think about it. It's written on the board. Okay. In our case, we just let the object roll. We just let the object roll. We didn't throw it. We didn't push it. We didn't pull it. We just put it there and let it roll. So we ourselves, the user, isn't putting any external force on the object. So why is it rolling? It is rolling because it has an mg sine theta force acting on it. So the forces that are along the x-axis is mg sine theta is equals to max. So that's easy. Normally you'll be able to normally it's a bit more complicated on what they want in the question, but this is a part of it. So from here you find out the acceleration along the x-axis, which is mg sine theta divided by m. Okay? Normally your math is finished here, but let's go to the y-axis. So along the y-axis, what forces do we see? It's the same. We see that there is an mg cos theta and that there is an r. One is downwards and one is upwards. So this brings me to the first trick, I guess. When doing this type of maths, always draw a free body diagram. What is a free body diagram? It's basically nothing. You just draw a Cartesian coordinate system. You assign the signs. Of directions. For example, in this math, I'm considering the left side to be the positive x-axis, the right side to be the negative x-axis, the upper side to be the positive y-axis, and the lower side to be the negative y-axis. You may even change this. This is the normal coordinate Cartesian system, but if you want, you can even change it. You can consider this as the negative y-axis, this as the positive x-axis, and this as the negative x-axis. In my case, I'm considering this. So we see that this is the negative y-axis, and the corresponding to this is the mg cos theta. And we see that this is the positive y-axis, and the corresponding force to this is the reaction force. So since this is positive, this one must be positive, and since this is negative, this one must be negative. So since this is the total summation of all the forces working along the y-axis of the object, we can write that the reaction force plus minus mg cos theta, because we have already established that any direction in this direction, any object or any force in this direction is the negative y-axis, and it will be negative. So this is plus minus mg cos theta equals to m-a-y. So we've done that, and we've pretty much finished our math. Hold on with me. Now we've already said that there is no acceleration on the y-axis, because our object is not moving upwards or downwards. It is only moving towards the x-axis. Since it is not moving towards upwards or downwards, then it must have no acceleration, meaning it must have no force, or it must have equal and opposite forces. So let's just write m into 0, because our ay is equals to 0. Or we can write that r minus mg cos theta equals to 0, or r equals to mg cos theta. Okay, so we find out the reaction force, but the question is, why did we find out the reaction force in the first place? To answer that, we'll have to add an extra force to this question, to this body diagram right here. But this is the basic math. If you understand this much, you're pretty much set for anything that will come in your exam question. So now in this system, we've only considered an mg sine theta. We've only considered an mg sine theta that works on the x-axis. But in reality, we always know that, there it is. We always know that a plane is not smooth. There are always some sort of grooves in it. Look at this wooden piece. This has many grooves in it, so it must have some sort of friction. Nothing in the practical world is frictionless. We only consider frictionless for mathematics, for pure mathematics. But in reality, this object has friction. If it didn't have friction, the object would have rolled much faster. So we consider that a frictional force is working on this object in the opposite direction that it is falling from. Why? Because frictional force always acts opposite to the motion. Since the body is rolling downwards, that means the frictional force is acting opposite, or it's acting upwards, or opposite to the object. Since it is rolling left, the frictional force must be working towards the right. So we've exactly just established that here, since it is rolling with acceleration a towards the x-axis, the frictional force is working against the acceleration on the x-axis as well. So it is directly opposite to the acceleration. So the y-axis is the same because no matter how much friction you put there, there's always going to be no acceleration on the y-axis, and that means there is no effect of friction on the y-axis, and so this will be the exact same for any math you do. But what changes is the x-axis, because we've already said that the frictional force works on the x-axis, not the y-axis. So let's just erase this part right here, and now we'll write the same equation again. Say with me. Summation of f of x of all the forces on the x-axis working on the object is equals to mass times the acceleration of the x-axis on that object. And so this is the part we focus on again, because this is the only part that changes in this math. So the previous one we had seen that only the mg sine theta is working on the body. But in this case we see that not only is an mg sine theta working on the body, but also a frictional force that is working exactly opposite to the mg sine theta force. So again, we look at the body diagram right here. We look at the body diagram right here, and we'll see which sign to use. Here, I will make a correction, and this is exactly what I've said to you a bit earlier. Normally the Cartesian coordinate system is this. The left is negative, the right is negative, the left is negative and the right is positive. But in this case, since the object is rolling downwards, for my own sake, I will say that the positive axis is downwards and the negative axis is upwards. This is an example, this is a golden example of exactly what I said earlier. I'm going to assume that this direction is the positive x-axis and this direction is the negative x-axis because that's what I want. That's what I want, not anybody else's wish. That depends solely on you and nobody else. So since we've established that this is the positive axis and this is the negative axis, we see that in the positive axis, mg sine theta is being acted upon. So we write positive mg sine theta. And we see that in the negative x-axis, there is a frictional force. So similarly, just like we did here, we say that plus minus Fk equals to MAX. So we say mg sine theta minus Fk equals to MAX. Now, we just isolate x, isolate ax. Ax equals to mg sine theta minus Fk divided by m. Okay, so in our previous example, we knew everything. We knew m, we knew g sine theta, we also knew m. But in this case, there is an unknown quantity, which is the f of Fk. So to calculate the acceleration along the x-axis, we have to obviously figure out what the value of Fk is. This, guys, students, is exactly where this comes into play. We know that the formula of frictional forces, of kinetic frictional force, I'll teach that in another topic, what static frictional forces and what kinetic frictional forces. The formula of kinetic frictional force is the coefficient of kinetic frictional force times the reaction force of that object. You see, this is where the R comes into play. UK, or the coefficient, is always going to be given. For example, let's just assume that it's 0.2 in our case. It's usually much less, but let's assume it's 0.2. So we can easily figure out what the frictional forces, because we already know R from here, and the UK is also given. So we can just input that here. Where's my pen? Okay. Or A of x equals to mg sine theta minus uk mg cos theta divided by m. Where did the mg cos theta come from? Because r is equals to mg cos theta. We just input mg cos theta into this, which goes into this. This is the complete, or 90% of all the maths you'll see. This is a complete overview, and this is what will mostly come on the exam. So how will it come on the exam is the question. Normally on the exams you'll see three or four different types of question. One will ask you what is the reaction force. One will ask you what is the frictional force. One will ask you what will be the force applied. Okay, let me just write it here. Boy, where should I erase? I'll just erase the free body diagram. One will ask you, let me just write it. One will ask you what amount of force should be applied so that the object moves downwards at 2 meter per second squared at any, let's say this is A, at A acceleration meter second squared. And the last type is, instead of downwards, we assume that this object is falling downwards, they'll just want upwards so that the object moves upwards and with an acceleration of A at 2 meters second square. So what are the types? First of all, reaction force. Second of all, frictional force. Third, what amount of force should be put on the body so that it falls with a certain acceleration. And the last one is what amount of force should be put so that the object rises up with a certain acceleration. I'll just post that on another video. This is the basic theory. Study it. Goodbye.